Ready.
Hi, boys and girls. It's the old man here today. What is a volt? Well, a volt is a unit of electrical potential difference. What is electrical potential difference? It's a difference in electrical potential energy for a charge from one place to another. And it's the change in energy per unit charge. It's joules per coulomb. And an interesting thing happens if we solve this for energy. Let's see, V is energy over the quantity of charge, right? I'm going to multiply both sides times Q. So this is just our definition of a volt solved for energy. How we doing? We all right?
Good.
What is an electron volt? You've heard the term electron volt, yes? What the deuce is that? Well, an electron is a charged particle, and as a volt is electrical potential difference.
Electron volt
is energy.
Okay.
Okay, so an electron volt is energy. All right, and it's a useful term of it. It's a useful quantity because especially things at the microscopic level when you're talking about electrons or protons, and it's appropriate to use in those situations. So an electron volt is a change in energy due to one electron being moved through a potential difference of 1 volt. I happen to have an electron here.
Oh.
If I take my electron and throw it into this capacitor, now notice I've taken electrons away from the bottom and put them on the top.
Okay.
So what's going to happen if I go in here? It'll be repelled from the top and attracted to the bottom. What do I have to do in order to move it to the other side?
You gotta do work.
I have to do work. Okay, how much work I do depends on the intensity of the electric field and the quantity of charge. And if let's see, electric potential difference is the work divided by the charge, yes? So if I move 1 electron through an electrical potential difference of 1 volt, I've done 1 joule of work, right?
Yep.
So therefore, work equals Q delta V, that's 1 electron times 1 volt. That's an electron volt. Now we could calculate how many joules. I don't feel like it. Okay, so 1 electron volt is 1 volt times the charge on the electron. And the charge on electron is 1.60 times 10 to the negative 19 joule a volt. 1.6 times 10 to the negative 19 coulombs. So 1 electron volt is equal to the same number.
Oh, I see. Okay, that makes sense.
All right. So it's a very small quantity, and in the physical universe, there are many instances where tiny amounts of energy are appropriate. So and then an electron has a mass of 9. I'm just going to put this over here. Mass of an electron is 9.11
times 10 to the negative 31st kilograms.
All right. Boom, boom, boom. Here's a diagram of the tube that's in this screen. It has in the back an electron gun. An electron gun that shoots electrons out towards a phosphor screen that when an electron hits it, photons are emitted. Okay? And so don't need to go into the function of the screen. We're interested in this and the deflection coils. These are magnets. These are electromagnets that you can change the polarity of, and you can change the intensity of. And so as the magnetic field that these make become more intense, you get a stronger force. So they come out with a certain velocity. The electrons have a certain charge. As you change the magnetic field, you can change the force acting on them, and that changes the amount of deflection you get. And watch what happens to the screen when I turn the television on. It'll only happen for a moment. Ready? You see that thing going back and forth like that?
Yeah.
That was the electron gun is still spitting out electrons, but the magnetic field dies. And so there are two sets of magnets, one that deflect them up and down, and another set that deflect it side to side. And you notice that we had a horizontal light beam.
Mm-hmm.
Okay, that means that the magnets that deflected up and down quit before the ones that did side to side.
I see.
So that's what's going on in here. Let's see that again. See that?
Yeah.
All right, and what that is that electron beam that, as we go into the future, kids will have no idea what the hell we're talking about.
Yeah.
Okay? So this television, this is not an unusual thing, has a difference of 7,000 volts between the anode and the cathode. What does that mean? You have a cathode which is negatively charged, and you heat it up and it causes electrons to boil off. You have an anode that's positively charged, so it's like a capacitor.
Mm-hmm.
And the electrons are attracted toward this, and they go faster and faster, and there's a little hole, and they speed out past this. So that's what makes the electron gun go. You've got a heater coil, 6.3 volts. I noticed that, and then so that's how the electron gun works. All right. So if you've got 7,000 volts from here to here, instead of 1 volt, you've got 7,000 volts.
Yeah.
How much energy does an electron have? So that's this is 1 electron times 7,000 volts.
Mm-hmm.
So the answer is
7,000 electron volts.
See how easy that is?
Mm-hmm.
That's 7,000 electron volts.
And if you wanted to change that to that, you would just multiply by the 1 point, whatever. 1.6 times 10 to
So
the...
what we want to do is we have 7,000 electron volts, and I'll use your meter. We need electron volts and joules on the top.
Mm-hmm.
And if I remember correctly, 1 electron volt is 1.60 times 10 to the negative 19 joules, right?
And we could calculate it.
Yeah. So 7,000 times 1.60 times 10 to the negative, 19. And that's 1.1 times 10 to the negative 12. 1.1 times 10 to the negative 12 joules.
Mm-hmm.
Now this is that right?
Yeah. Well, I mean, the setup is right.
Yeah.
7,000.
Yeah. No, it's
Yeah.
right. I'm just thinking of something else. All right. How fast is an electron traveling with that much kinetic energy?
1/2 mv squared.
So 1/2 mv squared is equal to the kinetic energy. We want to know the velocity. That's 2k divided by the m square root. So that's 2 times 1.1 times 10 to the negative 12. 1.1 times 10 to the negative 12 joules divided by the mass, which is 9.11. 9.11 times 10 to the negative 31 kilograms.
Sweet.
12 minus 31 is 19.
19, 20.
2
Yeah.
divided by 9, so we're going to be around 10. That's 2 times 1.1 times 10 to the negative 12 divided by 9.11 times 10 to the negative 31. And I get, holy shiza, 2.2 times 10 to the 20.
There we go. So how fast? That's fast.
Well, that's an impossible velocity.
Yeah.
The law, Einstein's relativity says that nothing can go faster than the speed of light, and that is considerably faster than the speed of light.
Yeah.
So, never mind.
So Mr. Boykin just chose some out of some unruly numbers.
Well, the numbers, are
made up.
Yeah, but I'm the teacher. I can do that. All right. So what we've got here, here's the heater.
Mm-hmm.
Here's the cathode. It's negatively charged. Here's the anode, and it spits the electrons out. These are focusing coils. It gets focused into a narrow beam here, and then here's a deflection. Okay, so if the velocity is this way and the deflection is up, which one's north, which one's south?
They're electrons.
So we need to use the left hand.
Yeah, electrons. Okay, so velocity is this way.
Velocity is this way.
And which...
the force is up.
Oh, okay, so... Wait. Velocity this way, the force is up.
So the magnetic field has to be out of the page.
Yeah.
See, there's two sets. There's one on the top and one on the sides.
Oh, okay, so...
So this is actually not a very good, I wonder if that other one has it on there. No, it doesn't.
So so go back to that one. What was your question again? It was which one's north,
Well,
which
what's the
one's south?
direction of the magnetic field that's causing the deflection? And the deflection is not produced by these guys.
North to south. It's this one over there is north, this one over here is south.
Yeah, so the velocity is this way. The force is up. So north has to be in and south has to be over
Gotcha.
here.
Okay, I was like, ah.
Okay, what effect will these have? Well, if the velocity is this way and say the field is up, then that's going to deflect it in.
Okay, yeah.
So,
So what's the point of making it go up? Why does it want to make it go up?
you want to scan the entire screen.
Okay.
This electron beam goes back and forth.
Yeah. Oh, and so it changes to make sure it covers the
It goes back
whole.
and forth 90 times per second.
Okay, I see.
All right, and what it does, it starts at that one corner, goes across, drops down, comes back, drops down, and goes back and forth till it gets to the bottom, and then it starts it all over.
Got it.
And so that's what makes the image that you see on the television.
Got it.
On the cathode ray tube.
Yeah.
A cathode ray tube?
Yeah.
CRT? Come on. Oh shit, I moved it. I'm not swearing on this video, am I?
It's alright. I'll be the only one who sees it. There it is.
Do it. Okay, so I have to come to the left.
There it is. And then twice. Yep.
Okay, if the electron encounters a magnetic field that's that wide, how much time will it take to go across going that speed?
Just be equal to d over t, right?
Yep. I had to make a mistake here somewhere.
Oh, you didn't square root it.
Aha! I was going to say.
I was like, wait.
All right, so second square. Thank you. Somebody's got a brain in the room. 2.2 times 10 to the 20. That's 1.5 times 10 to the 10, which is still too fast. So let's say the velocity is 1.5 times 10 to the 10. And I think what it is there's not 7,000 volts in that thing. 1.5 times 10 to the 10 meters per second. And if this is the distance, how much time? Time is distance divided by the velocity. Yeah. That's going to be point 0.15 divided by this number right here. Oh, that's going to be 15 divided by...
Is it 10? Times 10 to the 10?
No, it's going to be a very small number. So we got 15 divided by 1.5 times 10 to the 10. And I got 1 times 10 to the 9 seconds. 1.9 times 10 to the 9 seconds, which 10 to the 9... It's 10 to the negative 9, right? Yeah, 10 to the 9.
I was like, wait, that's a big number.
That's a long time. 10 to the negative 9 is a nanosecond.
Nanosecond.
So it's going to cross that
1.9
in a little under
nanoseconds.
2 nanoseconds. Okay?
If the perpendicular B field
Has a strength of 10 teslas, how much force is exerted on the electron?
Okay, well, we've got the speed, we've got the electron, and we're trying to find the B field. And we're trying to find the force, so we just use that one, BQE.
Yeah, so that's 10 teslas times 1.60 times 10 to the negative 19 coulombs times 1.9 times 10 to the negative 19 seconds, 1.9 times 10 to the negative 19 seconds. Times 1.0 10 to the negative 19. Oops, not divided by times 10. I get 1.6 times 10 to the negative 27 newtons. 1.6 times 10 to the negative 27 newtons. Okay, what the heck have we been doing? All right, we have an electron that is accelerated by the electron gun up to this speed. Mm-hmm. Okay, the magnetic field is
we used the wrong number for velocity. We used the time. We used seconds.
Oh.
I just realized that. We need 1.5.
So we should have 1.5 times 10 to the 10.
Yeah.
No. That's the wrong thing to erase there, Mr. Boykin. Okay. Because the velocity is, the velocity is 1.5. Hello. Times 10 to the meters per second.
There we go.
Somebody's got a brain in the room.
I was like, wait, hold on, we didn't use that.
10 times 1.6 times 10 to the negative 19 times 1.5 times 10 to the 10. .4 times 10 to the negative 8 newtons.
Okay. So now...
See how good it is to go back and think, now how did we get to this?
Yeah.
And find the silly mistake
I would not have caught that.
I made. Okay, so now we know the force, and let me write this down. It's 2.4 times 10 to the... Oh, I got it.
Okay, so it's the electron is coming out of a gun going a certain speed, and it's being influenced by
it goes through a magnetic field that exerts a force on it.
That's that much force.
What can you say about the direction of this force? Well, it comes out. We weren't given the direction of the magnetic field, were we?
No, just 10 Teslas.
We just got the intensity of the field.
Unless it wants us to look back at the picture. No.
Oh, what could you say about the direction of the force? Well, as the electron goes through in this, that force is going to be perpendicular to the electron,
yes,
which is going to cause
the velocity of it.
The velocity to shift.
Oh, I see. And create that circular.
Right. This is the force due to the magnetism, force due to the magnetism, and this is the velocity. And what does that force equal?
What is the shape of the path it will take? A curved...
It'll take a curved path.
curved path.
And we've already got that going
Yeah.
here. We could continue that. It'll be a curved
Mhm.
path. Okay.
What is the radius of the curvature for the path? Oh, we've got our B equals. Well, we have a radius up there, but
Okay.
oh, I
The
see.
magnetic force provides a centripetal force.
Yep.
And the magnetic force is equal to the mass times v squared over
Oh,
r.
there we go. There we go. I was like, we don't have current, so we can't use that one. So we just say that 2.4 number is equal to that,
So,
and we.
what is this? This is the force.
Mm-hmm.
So r is equal to m v squared over the force.
Yes. Bada boom.
So we could plug the numbers in here, couldn't we?
We could.
We're not gonna.
I was gonna say, do we need to? Okay.
Okay, so here's what we've got here.
Boom. There it is.
Here's the magnetic force due to a charged particle moving at velocity in the field. Centripetal force is our old friend. It's the mass times centripetal acceleration, which is v squared over r.
Mm-hmm.
What is a mass spectrometer? We had one in the chemistry department at Cal State Stanislaus.
I was gonna say we didn't have one here.
No, we don't have one here.
Oh,
Did you have one at St. Mary's?
Yeah, we had two, I think.
Yeah.
We had a couple.
Okay, so here's mass spectroscopy.
This is what I'm familiar with.
Okay, you've got your sample,
Mm-hmm.
and you have neutral molecules that come out under pressure, and an electron beam knocks electrons off of them. And so it charges them. Well, let's see. Does that electron beam? It all depends. So at any rate, it may knock electrons off. They may pick up electrons. Regardless, they become charged.
Mm-hmm. I can't remember exactly what happens. I just remember how we used it.
I think it knocks it off, because what you have here is you've got a positive plate that repels the ions, and negative plates that accelerate them, and they have a slot in them. So the neutral molecules come in, they become ionized by an electron beam. An electron beam knocks electrons off. They're repelled from the negative, attracted to the positive. They come out with some velocity. How fast they're going depends on their mass.
Yeah.
Their mass and their charge. Okay, so then you have the bending magnets here, and the amount of bend depends on the amount of mass.
Yes.
Okay, so as the mass changes, the radius will change. More mass, less radius. Less mass, more radius. Which is easier to make go around a circle? A bowling ball on the end of a chain, or a golf ball on the end of a string?
Golf ball.
Yeah. Okay, so what you then have is a detector, and what'll happen is you'll get a spectrum that represents the amount of deflection. And from the deflection, and usually what happens is the computer associated with the mass spectrometer does the calculation for you.
Yeah.
And
that was what we were.
Yeah.
That right there is my worst nightmare. Trying to figure out what freaking we were talking about.
You have this wonderful tool, but it doesn't do everything for you. All it does is tell you the mass. And if it's like an organic molecule that's got a bunch of carbons and hydrogens and oxygens and nitrogens.
It was like our worst night. We're like, we were just trying so hard to practice all the different things that we could figure out. It was just,
All right, so here's just something that you already know. Because the magnetic force on the electron is always perpendicular to the velocity, it doesn't do work. The force doesn't change the speed or energy of the electron, it just changes the direction. Okay? All right, so if the electron enters the electron field in a parallel plate capacitor, will work be done? Wait a minute, this is a different question.
I know, I was like, yes. Well, No.
Well, if you have an electron in a magnetic field, okay, it'll be curved.
Yeah.
Okay, but the force that caused the curve is perpendicular to the velocity, so it doesn't slow it up or slow it down, it just changes the direction. If we have a capacitor here, and we have an electron that enters, it's going to be...
Same idea.
So is work done on the electron?
No.
Yep.
Yeah, there is?
Yeah.
Well, because you have to do work to move it from one side to the other.
It produces a force that changes the velocity. For example, if it's not moving at all, is work done?
If it's not moving,
If it's not moving at all here and you let go of it, it'll be repelled from the negative and attracted to the positive, just like falling.
Yeah, so yes, work is done.
So yeah, its energy will increase, work is done. So this is an important distinction between an electric field
and a capacitor
where work is done and a magnetic field where no work is done.
Work is done on the charge to move it through the electric field in the capacitor.
Work is done to the charge.
Yeah, okay.
Okay, because it comes in with a certain amount of energy, and as it goes through, that force will be exerted on it and will increase its velocity up until the time when it smacks into this plate.
Yeah. A 5 kilogram mass on a 2.5 meter rope swings around a circle in 1.5 seconds.
Because we're the teachers, we're not going to do this. We will do this.
We'll set it up.
Yeah. This is 2 pi r over t. This is b squared over r, or 4 pi squared r over t squared. Equals ma equals mv squared over r, or
all that jazz.
Yeah.
Okay.
So all the stuff that's familiar, and this is familiar to the students. It's familiar to us. And now an alpha particle, we got exactly the same thing here. Okay? So, have an alpha particle travels in a circle where there's the radius and that's the velocity. So we've got the velocity, this, and we've got the radius. We can calculate the
centripetal
force. Centripetal acceleration.
Sorry, yeah.
That's my bad. So that's going to be 4.4 times 10 to the 5 meters per second. Square that divided by 0.012 meters. To the 5 squared divided by 0.012, and I get 1.6 times 10 to the 13. 1.6 times 10 to the 13 meters per second squared.
So it's a centripetal acceleration.
And then the centripetal force
is multiplied by the mass.
Is just the mass times the acceleration. It's going to be 6.6 times 10 to the negative 27 kilograms times 1.6 times 10 to the 13 meters per second squared times 6.6 times 10 to the negative 27, 7. That's 1 times 10 to the negative 13 newtons. 1 times 10 to the negative 13 newtons. What might provide the centripetal force?
Is it the B field?
Yes, absolutely. That's the only thing that'll make it go around a circle. You can't hook a string onto it.
Yeah, it's like gravity.
Yep.
What
magnetic field would produce a force on that alpha particle? I notice that I'm over here.
Oh my god, force would what would produce that force on the alpha
We
particle?
just
Oh,
calculated
sorry, yeah.
the force.
Got it,
We got
yeah.
the quantity of charge. We got the velocity.
Mm-hmm. Boom. Calculate it.
Want to calculate it?
Nah.
How much kinetic energy would they have?
Okay,
Boom.
then you just say 1/2 mv squared.
1/2 mv squared.
Okay.
How many electron volts is that?
Then you convert it to electron volts and you divide it by.
So what we have is joules.
Mm-hmm.
We have EV, joules, boom, boom, boom.
Yeah, just divide by 1.6 times 10 to the negative 19. If the charge on the alpha particle is a two positive.
Is plus, that's 3.2 times 10 to the negative 19.
Oh, I see. Okay. What voltage would be required to get it going that fast?
Oh, wait a minute. If we have electron volts,
Mm-hmm.
what voltage equals Q?
Earthquake? What voltage required to get it go that fast?
Okay, there's more to it than this. What is voltage? Voltage is work over charge, which is the energy. So we've got the energy. Energy field. So how much voltage? That's just the energy divided by the charge.
Oh, I see.
got
Oh,
the
I was
energy
looking at how fast. Sorry. What voltage?
So what we're going to have is we're going to have our answer in electron volts
Oh, it's joules per. Oh, I see. Okay.
divided by 2 electrons.
Yeah.
So
Okay.
we don't have to even use joules. We can use electron
Oh,
volts.
okay.
The charge is plus the same as on 2
I
electrons.
see. That makes sense.
Yeah.
The energy divided by the
Because
charge.
this is what we were using before, but we don't have that's the electric field. That's not energy. We had what is a volt? It's joules per coulomb.
Mm-hmm. And you could use the joules or the electron volt, really.
Yeah.
Yeah.
Okay. Now, if the charge on the alpha particle is this much, what strength electric field?
So we just.
So E is the force divided by the quantity of charge. So we've got the force from earlier. We just take that force divided by that many electrons, and it'll give us how many newtons per coulomb. Now, why is this important?
No. Do you know how to use everything? Oh, I haven't seen one of these yet. Today's a good day.
Particle with unknown mass and charge moves with a constant speed of that much as it passes undeflected through a pair of parallel plates, as shown above. That looks like a capacitor. The plates are separated by a distance of that, and a constant potential difference that is maintained between the plates. So we've got the voltage, we've got the distance, and we can get the intensity of the electric field from that, yes? All right. And a constant potential difference. A uniform magnetic field of magnitude 0.2 Teslas is directed into the page, exists both between the plates and in a region where to the right of them is shown. After the particle passes into the region to the right, the plates, where only magnetic field exists, its trajectory is a circle with the radius of this. See what's going on? Is it a positive or negative particle?
Give me a sec here. So we're going
Well, first of all, where should you look?
over here.
I agree.
Yeah. So
what's the direction of the force? It's toward the center, right?
yeah, so it's like this.
And what's the direction of the velocity?
So
you're using the right hand.
yeah.
So if the field is in, and it is, and the velocity is to the right, it can't be positive.
Yeah. Oh, I see.
If you use
So
your left hand,
and the force
field is in,
the field is in, and the
the-
force is that way.
and the velocity is to the right, then the force will be towards the center.
Oh, I see. Okay, that
So
makes
it's
sense.
got to be negative.
Yeah, it's got to be negative. Okay, that makes sense.
And then justify your answer, and you say, well, because it goes in a clockwise direction with the magnetic field in, according to the third left-hand rule. And although there are, I would say probably 75% more than that, never hear the left-hand rule. They only hear right-hand. Well, it's in the opposite direction of the right-hand rule.
Yeah. Okay, so, and then?
All right, so clearly show the direction of the electric field.
Okay, so so we've got two things happening here. We've got the electric field and we've got the That's why I was like, I've never seen a particle go straight through a capacitor, so some
a negative particle that's going in here like this. And so let me just put the particle right here.
Okay.
The force due to the magnetic field is down, right? Because as soon as it gets out, it does this. That means
they have to, if it's not going,
the electric field
they got to be equal and
has to be
opposite.
up.
So it's positive and negative.
So the question is, what's the direction of the electric field?
Oh, like it's up.
Yep.
Okay.
Determine the magnitude of the potential difference between the plates.
Ed.
Do they give us the intensity of the electric field?
No, but you might be able to. We can probably calculate it. It gives us the distance.
Okay, so we've got the velocity. Oh, what we need to do.
Oh, you can calculate it because it gives you the voltage and the distance. Wait.
Voltage and distance.
Yeah. Yeah. So the voltage is. Wait, does it? I thought I saw volts. Oh wait, constant voltage.
Constant potential. Okay, so it's not going to be that easy.
No.
All right. So, but here's the deal. We've got this velocity, yes.
Mhm.
And we have the intensity of B, don't we? Do they give us B?
B, yeah, 0.02.
So we've got velocity. We've got B. Do we know the quantity of charge on it?
Well, it's going to be it's an electron.
It's negative.
Unknown
We do
amount.
not have the charge on it. All right, so what we can do is the ratio between the force and the charge is equal to this.
Oh, I see. Okay.
See, and if you remember the Millikan experiment, Millikan could not come up with the charge. He came up with a ratio. He came up with a ratio. All right, so here, you know what?
What's our other equation for voltage? It's energy. It's energy over charge, right? No, we don't have charge.
Well, I printed out this solution, but
It's right there. See, right there. For a correct relationship between, so we got that, V over D. Between the plates, the electric and magnetic forces must be equal because it's constant. The electric and magnetic forces must be equal because that's what we talked about right here. For a correct expression relating the electric and magnetic fields, so earthquake equals QV BVQ.
Yeah.
Okay,
and
so
we were going there with that. That's where we were going.
So let's say, earthquake. We hadn't talked about. Okay.
And the force electric is, and the force magnetic is BQV.
Okay. Substituting for the electric field.
Oh, hold up. So go ahead, substituting for the electric field.
And solving for the potential. So V equals.
All right, well, check this out. Q cancels.
Yeah. Oh, nice. Look at that.
So BV is E. So this is BV. times D gives us a voltage.
BV. Wait, which?
Yeah, because voltage is ED, right, for the capacitor.
Uh-huh.
So these are forces.
Uh-huh.
The electrical force is earthquake.
Mm-hmm.
That's from this right here.
Yeah.
All right, the magnetic force is BQV. That's from this.
Mm-hmm.
So earthquake is equal to BQV. Now we've got the electric field.
Oh, okay.
Once we've got the electric field, and
Oh,
isn't
I
that what
see.
they're asking for?
Yeah, so yeah, okay, so you're saying, oh wait, you meant to put,
Now wait a minute. What are we asking for?
determine the magnitude of the
The
potential.
voltage. So we want is volts.
They
so-
said to make this V for volts. Because they want voltage.
Well, they've got VBD.
Oh yeah, the
So
VBD.
VB times the distance. So what we did is we put this right. So there it is right there.
Oh wait, sorry, I'm just having a hard time seeing it. Okay, so V and D.
No, V.
Sorry.
Here's V is ED. This is a capacitor.
Yeah.
And if we know the intensity of the electric field, they give us the distance, we can find the voltage.
Uh-huh.
How can we find the intensity of the electric field? It's from this right here, from the forces.
Oh, B and V right
So
here.
we've got
we put
two
these
things.
BVs
We've got-
right there. I see.
We've got this fundamental thing about a capacitor. No, this is the definition of the electric field, and this is a capacitor. So we've got these two things
Yeah.
going on.
Okay, that makes sense.
So we use this,
Earthquake
yeah,
for
earthquake
the force there.
for this, and we use this for the magnetic field.
Charges cancel.
Charges cancel, so E is equal to BV. You just put BV in here for this times D, which is what they've got.
I see. Okay, and then you solve for it. Determine the ratio of the charge to mass. Oh, you just do Q over M, right? Well, our charge. Oh wait, we don't have our charge yet.
What's
Wait,
the
do we have a
ratio
charge?
of charge to mass? All right, so charge to mass is going to come from this. So
Well, so if we have the electric field. Do we? Oh no.
so the force centripetal is provided by the magnetic force. This is mv squared over r is equal to bqv.
And there's our little charge hanging out in there. And there's our mass. So do we
divide
just
this by, they want mass to charge or charge to
charge mass?
Okay, so we divide both sides by BV.
When you put M over there on that side.
Oh, I left mass out.
Yeah.
So, and then we divide by mass.
Yeah.
So
You're
that's
there.
V squared over B velocity radius. And they
And we
give
have
us the
all.
radius.
They give us all those.
We've got the velocity. We found did we find
They,
the
they
magnetic?
give us the B.
They give us the
magnetic
magnet, and then they give us these. So it's just boom, 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 is equal to Q over M. And that's important because that's what, what's his name did. All right, and that's it.
field. Cool.